So, kind of about a little bit about myself. I've already introduced myself, but I'm Todd, first year graduate student. I work with Mike Newchurch. I actually got my bachelor's here at UAH, so I guess I decided to stay. And I've been doing balloon launches since high school. I think my first balloon launch was launching a cigar box with an old iPhone. So I got a new iPhone. I was like, I have this old iPhone. What do I do with it? Let's throw it in a cigar box and fly it. So
You're one of those guys.
yeah.
Expensive payload.
So I'm involved in a lot of different projects. So obviously balloon chasing, is pretty cool. Like I said, I have a lot of work here at UAH, involving air quality. This is actually with the truck that we do. It has an ozone LiDAR in it. I'm here with Mr. Chris. We do a lot of lightning payload launches. It's pretty cool looking at radiation thunderstorms. We're going to have a demo after lunch for this project. This is a thruster balloon payload, so it has compressed air. It can spin and point at different things. And I'm also involved in the severe weather side, so we go out and chase the storms and deploy the balloons in front of the storms. So, yeah, it's a lot of fun balloon stuff goes on at UAH. So if you have a kid who wants to get in balloons, send them to here. Right? So just to talk about this, I think we all know about Pico balloons, right? I mean, this is kind of a very common thing now. Thanks to a lot of people in this room have made Pico ballooning kind of more accessible to everybody. So this was around, gosh, I think 2 years now. We did 3 flights from UAH, the original Northern Hemisphere flights. We flew on SBS-13 balloons, and we flew Bill Brown's Sky Trackers, 20-meter Whisper. So this was a really successful flight. The one that stayed the longest was 6 months. So we actually turned this into a paper where we actually use these to evaluate meteorological models. If you've heard about high split, we actually work closely with the high split team for this study right here, which was actually published in the Bulletin of American Meteorological Society, to evaluate trajectories, right, that you generate, right? When you run your balloon trajectory, you might visually look and see how it did, but like what we did was we actually calculated how well they did. So actually mathematically published those results. So we did stuff like running trajectories while the balloons went over the Himalayas and comparing when the model was good, when the model was bad. So that was a really cool study. So how did I get to Antarctica? I think the first thing that I was wondering is we actually flew during the Northern Hemisphere flights. This was one of the trackers we were flying. We flew Bill's call sign. Sometimes you'd hit this station out here, right? And that's a long way to travel, right, for a little Whisper tracker. So what's going on down there? So this is near Meyer Station. Y'all might have seen this. This is actually a Whisper receiving station that was set up, I think, in 2017 for a large, I think it's 11-year sun cycle study that's looking at propagation lower latitudes. So I was like, hey, they have a paper on this. They're talking about their objectives. So why not submit a proposal and kind of team up with these people using these Pico balloons, right? So I submitted a proposal under these 3 research questions. Of course, how do micro superpressure balloons behave in Antarctica, right? It's pretty cold. Looking at 20-meter Whisper propagation, we're talking about Antarctic summer, so the sun never sets there, right? So that's really convenient for a tracker that's solar powered, right? It transmits 24/7. And how do looking at NOAA high split trajectories perform in this region, just like we did the study before. So the first thing, I think we launched 8 total. Is that right, Bill? Yeah. Everything was brought in my hand luggage, right? So that's amazing. You think about these bigger super pressure balloon flights, right? Will this have fit in my suitcase? I don't think so, right? And I mean, how much helium do you think it takes to fill that balloon up, right? Millions of dollars worth of it. I mean, you got a crane out here, you got trucks, you got all these people, right? So the main research thing that I was putting out was, hey, we have these balloons, we have these trackers. Let's see if we can do this at a really cheap cost, right? It's probably around $200 per launch. So That's cheap compared to this. And that's multiple launches compared to this multi-million-dollar one launch, right? So that's kind of what I was putting out. So I put that proposal in and it got accepted. So they're like, hey, come on down. We'll fund your station time. And so, yeah, and of course I talked to a lot of the meteorological PIs and the whisper people, and it's good to have your name out there before you submit these proposals so you can kind of get in with the crowd, I like to say. So what we did before, we actually pressure tested Yokohama balloons. This is kind of a little diagram how we've done the pressure testing. So we pressure tested, I think, 10 in total. We brought 10. And this is kind of how we did it. We just had hooked up to an air compressor with a manometer measuring pressure. And what we found is we did a lot of these pressure tests is when you really want to pressure test those balloons to around 0.4 psi. So this is kind of an example. The first thing you do is you burst one. You fill it up to where it explodes. It makes a really loud boom, and everyone runs over to you and knocks on your door and thinks someone got shot. That's what happened when we blew up one of these balloons. But you figure out the burst pressure first, right? You want to see where your balloon bursts. And then typically what we do is then we pressure test it to around half. Because you really want to be able to pressure test it so much that you're not overstretching it. So when it gets up, the balloon just does this and it keeps stretching back and forth. And then it rips and bursts and comes down. But you don't want to pressure test it so little where you're rising too fast and you're expanding too much. And that stretches the balloon too much. So you got to be in that nice little golden range that we've seen for at least these Yokohama balloons, where you're right in a range where you're not going up too fast and you're going to burst, and you're not oscillating back and forth and stretching out the membrane, and your flight is over in like 3 days. So that's kind of what we found. We had these little ranges we defined. This is we've done a lot of stuff like flow calculations and stuff. This is just the flow chart. I could talk more after this about this process. We actually have a paper that we just submitted to JTech over at AMS that describes the full Pico ballooning process. So if y'all are interested or anyone's interested, I can send you the first draft manuscript for these. And then what you can do is you can actually make this, I call it a likelihood to succeed chart, where you actually plot internal balloon pressure on the X and your free lift on the Y. I think a lot of people have done Pico ballooning know that the free lift fill is the most important part of a Pico balloon. If you mess it up by 2 or 3 grams, that thing's going to burst and it's going to come down. So this is kind of a good way you could do this for any balloon. Like get a balloon, go to a party store, you could go through this whole process, right? And figure out if that balloon could be used as a Pico balloon, right? You can go through the whole process, do all the calculations, and figure out, is it going to succeed? And you want to be in this green region with the X. So you can see the project balloons that we flew for Antarctica were right in the green region. So this process works really great. And we've had really good success with these. So
Todd, for the Yokohamas, between 6 and 8 grams is the ideal free lift.
Yeah, correct. So you can see, that's what we plotted for there. So you don't want to be too low, and you don't want to be too high, of course. The risky, I included the risky. I didn't want to include just like, oh, this is a high probability of doing well. There's also a risky region. Like if you really want to fly higher, you can put more lift in it, but it's risky. It's on the, could burst. It could be too much. So you can live on the wild side if you want to do that. Some people do. So yeah, let's get back into it. So how did I get to Antarctica? Everyone asked me this, like, what was the process? So I just made this map. Left from Huntsville, went to Georgia, landed in Munich, then flew to Bremen. I quarantined in Bremen. This is kind of when COVID was still, running rampant. Oslo, Prague, fuel stop in Chad, Africa. We stopped for the night in Cape Town, Africa. Then we flew to Troll Station, which is, I call it the connecting airport of Antarctica. That's what everyone calls it. And then to Niemeyer. So that was 9 total stops. And it took around a week to get there. So the flight from Troll Station to Niemeyer Station was in a little tiny prop plane that it almost looked like a cargo plane. that had skis to land on the ice. I'll show you some photos. So yeah, that's the plane, the right all the way at the bottom that took us to the station. Here's some really nice photos. This is actually first getting to Antarctica in the big Boeing. And we literally landed like right on the airfield and just got out in the plane. So
What was the temperature?
it actually wasn't that bad. It was summertime. And when you're in the polar clothes, right, it's always below zero, right? It's always below 0 Celsius. Below freezing, but the sun just beats on you, and all the white and all that solar radiation just reflects and just heats you up. What really gets you is the wind chill. So if there's low winds, literally I walk out, you'll see a picture in a t-shirt, and the meteorologist, he would launch balloons in flip-flops.
Wow.
So eyes.
Yeah.
That would be hard on the eye.
Yeah, oh yeah, you always had to wear sunglasses usually because of the UV. So that's our Moore station, more photos. So this is the station. This was actually the last sunset before a polar day. We had ski-doo training. That's how we got around. It was kind of fun. We drove around in cool ski-doos. And we're actually, near Meyer Station is right on the ice. So the water's there. I mean, you can see the glaciers that are just sitting in the ice. So we're right on the border. So really good. So now let's talk about balloons. So I kind of made a checklist for myself for launching these people because y'all know that these things are pretty small. And if you have a lot of wind, especially with the 20-meter antenna, it's a pain to get off the ground. So surface winds, I said to myself, below 10 knots, no clouds or a cloud layer with thickness less than 500 meters. And then a high split simulation show a safe 5-day flight from launch. I'll talk about that in a second. So those were my 3 parameters for these flights when I was down there. I had to meet all these before I chose a good day to launch. And sometimes it was really hard because sometimes it'd be like 30 knots outside. I mean, there's no surface friction. The wind just gets up and it's just really windy. So finding that slower wind day was really important. So I actually wrote a whole process to run high split trajectories on my computer back home and post them to Twitter to a automatic bot to know when to launch. Because I was afraid if I got down the station, the internet's not that good to be able to download gigabytes of meteorological data. So I just ran it all back here and I knew I could probably get on a social media site at the station. So I just did this. So this basically would run a high split trajectory and make this plot for me for every single launch window. It was actually a gift. So it's really convenient. So I'll show y'all. This was, so here's an example. This is an unsafe. I would not launch on this day. And the key is looking at this right here. This is actually trajectory rainfall outputted along the trajectory. Pico balloons do not like when you're over areas a lot of convection, when there's a lot of updraft, a lot of vertical motion upward. So if I had a lot of rainfall, I kind of didn't want to launch on those days. So I ordered those. Also, I ran trajectories on different surface types. So there's model vertical motion, isobaric vertical motion, constant density surfaces, and then isentropic surfaces. So it creates kind of an ensemble of things. So I would not launch on this day. I would launch on this day. So this is a good example of one I launched on most all days that look like this. I wanted to keep them over Antarctica because it's cool. I wanted to stay over Antarctica as long as possible. So this was a really nice day, low surface winds, very little precip. Typically, I always want to be below 1 millimeters per hour, and usually the Pico balloons are safe if you're below 1. So yeah, that's the model. So those were posted to Twitter, this little Twitter page, every single day. So I just was like, okay, what's the launch look like for today? They did it all automatically. So that's how I kind of figured it out. So let's look at a launch. So very calm winds on this day. I was very lucky.
Yeah, because
And no trees.
No trees, yeah.
No trees.
No.
Flight string?
What was that?
How long was that flight string?
How long in their antennas, Bill? It's just
That's 17.
17, yeah.
The 1 inch up, 17 feet, that's
Yeah.
1 inch down, and about a 3 foot connecting line to the balloon.
Can y'all see it?
Yeah.
Yeah,
Yep, there it is. So this was a clear day, literally not a cloud in the sky, and you can see a little dot. The air is so clean, so pristine. You could see for so really far on a really nice day. Just like no pollution. So here's some other photos. So this is actually, they launched their weather balloons at the top of this station. So this is where I filled the Pico balloons up. This is actually the meteorologist behind there reading a book outside, just up there hanging out. So I was filling up this balloon, and here's another balloon launch that I did. I have a lot of photos, talk forever, but yeah. So here's one of the sky trackers. I actually filled 2 balloons up right there, so that was right before launch. I typically filled them up and the day before, and then came back the day of launch and measured their lift again, make sure no leaks, and then I flew. So I left them up in the balloon place for the night. So this is in the paper that I recently submitted to JTech. This is just showing all the ascent rates of all the balloons. And also, so the bottom plot right here is ascent rate versus time since launch. So you can see that the balloons, their ascent rates are pretty consistent between all these days. And then they all drop to an oscillatory float range of between negative 0.2 meters per second to 0.2 meters per second, which is nice. We did have a leak. We think it was a little faulty balloon, but all the other balloons floated successfully. So yeah, but you can notice it floated for a little bit. So something must have happened with the material. Usually if it's a failure, it like comes down immediately, but this kind of floated and then it leaks. So it was kind of interesting. So yeah, here's the trajectories from the 6 balloons. Like Bill said, we still have one flying actually, but it has a faulty GPS. So it occasionally transmits its location, kind of comes in, comes out. Last time I checked, the last update was a day ago. So that is still up. We just don't know exactly where it is.
Right.
It's in some giant box. So it will occasionally say hi and then it will go by. Yeah, yeah.
You can get a sense of where it is by the time it turns on, the time it turns
Yeah.
off. You can get a rough estimate of.
Yeah, the solar elevation. So yeah, this is very successful. I mean, this is all from my hand luggage, right? So that's, again, that's what we were marketing is cheap, low cost balloon flights for scientific, exploration in remote areas. This is 6 flights, right? And all in a suitcase. So that's pretty incredible. It really is. Oh, thank you. So this is just some preliminary model experiments. What we've actually done is first, there's a separation experiment I did. I deployed 2 balloons at the same exact time. I wanted to see how long it took them to drift apart from each other. So top plot is latitude versus time. So you can see they stay together for a while. And then a few days later, they actually separate. One takes a trip to right by the South Pole. And then they end up coming back together to meet up. One takes a shortcut, if you can believe that, which is actually incredible. And you can actually see when they start to separate, if you look at the percent error of a global data assimilation model, there's actually a lot more error when those separation happens, which is probably due to some sort of turbulence effects or slower velocity flow that the model can't pick up. So that's pretty neat to see. So the balloons actually came back together and then they stay together for a little bit and then they separate again. So for reference, 10,000 kilometer distance is approximately the distance from the South Pole to the equator. So those start to really expand like really far away from each other. Where one's on the other side of Antarctica. And so really far. So that's some preliminary data. We still got a lot to do. Look at that. Now Whisper. Okay, so like I said, there's also a propagation study, right, that we want to do. Whisper propagation is very cool, very unique over in Antarctica. So these transmitters are not putting out a lot of power compared to like surface-based stations, right? Surface-based stations have much more power compared to our transmitters in the air. But look at this. I mean, we're hitting contacts. I mean, almost every single continent over Antarctica from that little tracker. So it's very unique. You can send signals pretty far. We actually have another paper in review that's looking at polar day Antarctica radio propagation. So also some preliminary plots from this paper. This was just submitted to what journal is it? It's a special issue of ionosphere techniques or propagation techniques. So this is actually two maps of left is the balloon locations and signal travel distance. It actually shows the signal for each grid square, the farthest the signal was sent. And then the right one is actually the signal to noise ratio of each individual signal. And you can see, obviously correlated when you're closer to Australia, your SNR is higher, right? There's more of a whisper receiving network to hear your stations, right? So you can actually quantify where the balloon is going and how well the whisper network is doing, which is really neat to be able to do. Whereas the surface station it's only one point, right? So you send out a signal and that's just one location of profile. Instead, we're looking at it as a function of where we're going for each individual transmission, which is typically not what whisper is used for. Typically, it's a surface station. So this is a really cool way to visualize data. So you can also see that Niemeyer station does really well with decoding the signals as well. There's higher SNR around when you're closer to the station, which makes sense, right? Now this is really cool. So what we actually did was we calculated the solar elevation angle at the location of the balloon for every single transmission throughout the whole study period. And then we look at how far the signal traveled. And we do a 2D histogram. I call it a spot 2D histogram. And you're actually showing a distribution of different characteristics. So for instance, you can see right here that the signals that travel farther than 7,500 kilometers, the solar elevation angle had to be below 50 degrees, right? So that's really unique, right? So that's those long signal hops that we're talking about. So we've actually shown that there needs to be a certain solar elevation angle throughout all of the lower latitudes and over Antarctica to get those really far signal hops, which is really cool to see. You can also see this distribution range right here. This is mostly attributed to closer stations like the Australia stations, South America, Niemeyer as well, that was decoding. And those are those short propagation hops. So not the long ones. So those are the ones that spent less time in the ionosphere to be decoded. So that's kind of interesting. And then this blob right here, this is interesting. If you calculate the line of sight range of the balloon and the extent of how far the horizon is, this is the line of sight transmissions. So this is when the balloon was directly over a whisper station. So that's where that frequency blob is right there, which is really cool to see as well. Because where the balloons are, they have around 400 kilometers line of sight to, you can do a circle. I think y'all have seen on HabHub, they have a little circle. That's the line of sight to the horizon. If you calculate it for a balloon floating at 12 kilometers, it's around 400 kilometers to the horizon. Now, this is another cool thing we did was we calculated the solar elevation angle for both the balloon during the transmission and the solar elevation angle for the whisper station receiving the balloon transmission, right? So you're looking at both where the signal was sent and where it was received. And you can do the same thing for a spot 2D histogram, and you can kind of break this up, right? So this distribution right here is actually Niemeyer receiving all these transmissions. Notice because it's between 0 and 40, which is the solar elevation angle for the station because the sun never set. So you can actually see those are all the Niemeyer station decodes. And then you can actually see there's another distribution range right here. We think that is possibly lower solar elevation angle propagation as well. But this is actually a 1-to-1 line showing if the RX solar elevation angle matches the TX solar elevation angle. So you can see if the transmission was sent through the day to nighttime boundary separator, which is a really cool method of doing that. And then of course you can also see, if you look at the TX solar elevation angle, there's a kind of a white area there too. So that means that the TX, remember the transmissions only happen during the daytime, right? So this says for solar elevation angles above 40 degrees of when you set your transmission from the balloon, no, they were only received by stations where it was nighttime, right? Because this is 0, this is daytime for the receiving stations, and then this is nighttime. So you can see it's a lot to talk about. I could talk about it even more, but these whisper balloons are really, really nice, right? Because you're traveling to so many different places. You can assess ionospheric propagation in a really broad range compared to one site that is specific to that one area, right? So a lot of cool data from those flights. All right, so I want to talk a little bit more about life at the station, right? Because Antarctica is pretty cool. So this is actually me launching one of the 12Z soundings. So you can see I'm in a t-shirt. It's nice and warm. This is really cool.
Launch them when? See that.
So yeah, those launches were typical windy, cold. That's when you had to get in more. You can't just be in a t-shirt for those. But that person, those two people you saw, that was Marcus, the meteorologist. So he does a balloon launch every single day.
Wow.
And they're called overwinterers. He is stationed there for a year. He does a balloon launch every single day. So kind of a cool job, right?
Literally.
Anyone want to sign up?
Yeah. I go.
Yeah. So penguins, right? I want to show some nice photos. They just make you feel warm inside when you look at these things. So because Niemeyer was right on the ice sheet, basically, there was a lot of marine life. So we literally drove up to a penguin colony. They're really friendly. They have no natural predators on the ice, so they'll walk up to you and peck your boot. So they're so cute. So I have a lot of penguin photos. I think 75% of the photos I took were of penguins. So yeah, that's a good selfie. Oh yeah, a lot of those. Some other life at the station to wrap it up here. So this actually, I had a roommate. He was from Norway. He was there to repair this truck right here. So we drove out on the ice, and you can see how big these tires are. These things can really take a beating. So he fixed one up, and we drove all around. We went to the penguin colonies and all around the station. So they had a nice break room. They had a pool table, coffee bar, actual bar. There's some photos I can't include on this presentation. So we had movie nights. A lot of the movies were in German, but oh well. And then we gave science talks. This is Marcus. He talked about snowflakes, and some people talked about seals, and I gave a talk on the balloons. So it was a great one.
Todd,
Yeah.
were you able to communicate with the college too, to do your other studies for your other?
Well, it was during my break.
Oh.
So it lined up pretty good. Yeah.
Yeah, that lined up really well.
Yeah, it did. So good food. People think, what were you eating? Like canned sardines or whatever? Like, no, they had a full-time chef, and they really, really good food. So coffee every day. Sometimes you go down to the kitchen, he just make a cake and just be there. You can eat it. Because it was polar day and the sun never set, everyone's sleep schedules was all over the place. So you could be up at like 4 a.m. and somebody would be cooking in the kitchen, because that's just their schedule. It's kind of interesting. So this was really cool. This is actually because Niermeyer is actually on the glacier. So it's designed, you can see it's on stilts. So they actually have to put snow under the station to keep it from being buried. So the station itself moves with the glacier. So it's not a stationary station. They actually have to update their latitude longitude coordinates every year because the station is moving. So the Met station gets buried over time. So we had to go out and move the 3-meter temperature probe up because it was buried. So he's actually measuring it. So we went out probably on the windiest day there. It's not, it looks nice out, but this was like my eyes it was so windy. So yeah, that was pretty cool. They had a wind turbine. That was pretty nice. This is actually the glacier, and then this is the sea ice. This is right on the border. So that was a really nice day. Nice photo. All right, so that's it. I just want to thank a few people. I know everyone's probably hungry. Dr. Nutcher, she helped me a lot getting there. Bill Brown, of course, with all the trackers. We couldn't have done this study without him and got all this incredible data and all these awesome publications out. And I also want to thank, there was some travel costs. AES department, ESSC, College of Science, and the Space Harbor Club all pitched in some money just to get me down there. So yeah. So thank you guys. Anybody have any questions or anything?
Well, I just wanted to mention that part of Todd's donating part of the balloons down there for off the raffle.
Yeah, we have some Yokohama balloons that I actually pressure tested with the process I described that we're raffling off. How many are we doing, Bill? I think 2 raffles.
How many do you have altogether?
We have 6.
Need 2 for the flights tomorrow, 1 spare. We'll probably raffle 2 off.
2 off. Okay. Cool.
And then the trackers, didn't you?
Yeah, so we also have IMET-1 radio sound trackers. They're actually discontinued. We've flown them before. One of them has a broken temperature probe, but they're great for trackers. So if whoever wins those is free to mod them or do whatever. They're really nice equipment. All right, any questions before we go on? I got one over here.
So when you're looking at what to research with commercial items, a lot of times they did pretty well tested in the lab. Did Yokohama not share their data with you, or how'd you find a niche they hadn't looked at?
So Yokohama balloons are literally party balloons. So literally, it is a party balloon supply store. It is not. Yeah, they're not producing these balloons and saying we are selling these to the Pico balloon community. That's no. We figured out that Yokohama balloons are great for what we do for Pico ballooning, and we have refined the process of pressure testing. And that's hours and hours in the lab, seeing what works, what doesn't, what pressure test range work, and just making it work. What does the data say? How can we get them to float? So that's how we've refined the process. It's not calling up Yokohama and saying, hey, how do you float a balloon at 12 kilometers? They'd be like, what are you talking about? We're selling these for birthday parties.
Birthday parties,
Yeah.
kilometers.
Yeah. But it's crazy because it is a party balloon. It's like $2. And if you do it right, you can turn it into a scientific pool for a really cheap amount. So it's really nice.
What about the SBS balloons? Was there ever any acknowledgement of failure on those on their part?
I don't think they ever acknowledged it, but I will say we have.
I can address
You want to address that?
They have, if you pressure test them first,
Yeah.
then your likelihood of failure is very, very low. So they are working on a procedure for pressure testing just the same way we do the Yokohama balloons. The ones that stayed up for over a year, those are all pressure tested SBS 13s. So pressure testing is the key no matter what balloon you fly.
So pre-stress screening.
Now, I will say that the Yokohama, the new batch of Yokohamas is 6 grams heavier. And so it'll fly lower, and it looks like a different material than the older version. So just so you know, we have had successes with the new batch, but they will fly lower. because they're just heavier.
Question?
I got 3 questions.
Sure.
They're all real quick.
Okay.
One, where do you get those balloons at?
It's literally called Yokohama Balloons. Just look it up. It's a balloon company.
Oh,
Yeah,
okay. So you
and-
order it from them?
Yep.
Okay.
You order it from them, they'll sell you a minimum of 10 and they'll charge you $100 postage, but you'll get it 3 days after you order it, all the way from Yokohama.
Yeah.
Okay.
But I will mention that Todd and the students here at UAH they have a batch of them that they will sell pressure tested to help with their finances at their club activities. And it's what is it, $30 just for the untested balloons.
Yeah.
And since it takes about an hour or two to do one, we figured about $50.
Yeah, that's what we do.
It's $50 for a tested Yokohama balloon from Todd. You can order it directly from Todd.
Cheaper than an SPS 13.
Yeah, because they're $50 plus. But if you want to pressure test your own, I can show you after lunch how to do it with a tire inflator deflator that costs 50 some bucks from Harbor Freight. And then you just get the $30 price. They're $18 a piece plus the $100 postage.
Yeah. So
by the time we send it to you, that's another $10 postage. So at $30 is breaking even.
Any other questions?
But that way you only have to do 1 balloon or 2 balloons instead of buying 10, paying that exorbitant fee.
How many people were at the station down there with you?
So I went by myself to do the balloon launches, but staff at the station, it was only around 20 people, 21, 22 people. The station is, I mean, it's probably one of the smallest stations out there in Antarctica. Niemeyer is very small. So compared to like McMurdo, which is the US station, I mean, gosh, they have 1,000 people during the summer sometimes. It's literally like a city. This is just the station and then nothing. So if you walk 10 miles out, you could just vanish. There's nothing there. Yeah. That's your question?
What are they doing for power down there? You showed the terminal.
Yeah. So they have 2 massive generators to power. They have solar panels on the roof actually. It's actually on the side. There's a photo that shows some, and they have the wind turbine. So the generators, they're very particular about how they do that because they actually have a station that does chemical measurements and species measurements, and they built that station specifically from away from the main dominant wind direction, so that plume of NO2 from the generator never goes, or very rarely goes, to the chemical station. That's literally like you got to walk to it from the station. So yeah, so 2 generators, big massive generators, turbine, and solar power. So mostly everything. Yeah.